seriously, every time it looks bigger. It just looks bigger. Hi, everybody, and thank you so much for attending this session. My name is Saar Amar. I am a security researcher at the MSRC. My whole life is about reversing and exploiting vulnerabilities. I'm also highly addicted to CTFs. I play with Posten, which I hope that you heard of us by now. And here, well, we have so much content to cover today, so let's just get right into it. As you all know, we have this huge memory safety problem. We've built our entire ecosystem upon unsafe memory languages, such as C and C++, and this, of course, introduces many memory safety vulnerabilities. And the problem is that you cannot just throw away all of this legacy code, because it's just too expensive, it's unrealistic. And this is why we have mitigations. And in the past 2 decades, we've seen a lot of software mitigations, which is really nice. But in the past few years, actually, we've seen a lot of hardware-assisted mitigations, which is fantastic. The reason that mitigations at the silicon level are so powerful is because, well, first of all, we get much better performance because the new piece of logic is actually implemented at the silicon level, and it's not just another layer of software. And because it's not just another layer of software, we have much more power and much more abilities than we had before. Here is a short list of some great examples for hardware-assisted mitigations. We have no time today at all, so let's just get right into MTE. So, memory tagging extension. As you all know, sorry, so MTE adds a new type of memory to the ARM architecture. It's supported only on like 64 bits, of course, and basically this whole new thing of MTE comes down to the following. Each 10 hex line of physical memory line is assigned with a tag. This tag is just a numerical value, 4-bit size, so we have 16 different possibilities for tags, and the way that it works is that each pointer that points to a virtual address, that maps a physical address from this new type of a memory, has to be a tagged pointer, which means that we encode some bits, some information in the unused bits of the pointer. And in this case, we just set the tag in the most significant byte, in the MSB. And now, every time that you dereference some address, every time that you do load or store, the architecture itself, the CPU, will compare both of these tags. The physical tag from the underlying physical memory, and the logic tag from the MSB part of your pointer. And if these two pointers are different, an exception will be raised by the CPU. And here you can see a very simple illustration of that. So on the right-hand side, you have your physical memory with these unaddressable tags. These tags could be only modified via a specific set of new instructions. And you cannot reach to this memory area via the page tables and etc. And on the right-hand side, you have your virtual addresses, which just are tagged pointers with these tags at the MSBs. And if these two tags are different, an exception will be raised. Okay, so this is really cool, but clearly you cannot just dereference these tagged pointers, right? They are not canonical addresses. You will segfault. These tags at the MSBs will mess up the other address translation process. And it's unacceptable to expect people to do all of these bitwise operations before every single load and store. And this is why we have a great CPU feature from ARM called TBI, or Top Byte Ignore. This feature does exactly what its name suggests. When you enable this feature, the CPU just ignores the most significant byte in every pointer. And this is exactly what we need, because it means that the tags won't be into account into the address translation process. This is from the spec of ARM. I highly encourage you to check it out if you haven't already. Okay, so far, it's very simple. ARM proposes 2 modes for MTE. You have synchronous mode and you have asynchronous mode. Each mode clearly has its own pros and cons. And just before we are gonna go into detail, I just want to mention here that you have full control over the configuration of this per process. So you can have one process with synchronous mode and another process with asynchronous mode, and everything works. So what is synchronous mode? With this mode, you have this guarantee from the architecture that when some instruction violates memory tagging, the CPU raise a synchronous exception on this very specific instruction. This means that you have this guarantee from the architecture, from the CPU, that this instruction cannot retire. It means that no further damage could happen. And it also means that we have accurate information on the crash. We know exactly which instruction faulted. We know exactly what the start of the registers and the call stack and basically everything. And while there are many upsides here, the one major downside is that this mode is probably less performant, because load and stores cannot retire until the tags are being read from memory and checked. Okay, we also have asynchronous mode. With this mode, we have no exceptions. Here, the CPU just sets up some bit in a system register when it detects a memory tagging violation. And it's the job of the operating system. It's up for you in your code to periodically scan this register and look for asynchronous issues. Clearly, in this mode, the faulted instruction could retire, which means that further damage could happen. This is really bad news from mitigation development point of view, because you clearly have this window to race. And also, you have no accurate information on the crash whatsoever, so it's really funny. You know that some thread or some process has crashed at some point in time, but you have no idea where, why, how, what's going on here. And while there are many, many downsides here, there is one major upside, that this mode should be much better performance. Now, I also want to be fair and to mention that you can create some really interesting properties out of this mode, right? If you just modify your thread context switch mechanism, and you'll make sure to loop up for this bit, you could create this really nice property that memory tagging violations will be detected until the next context switch, which is a fair property to have. And now that you are all super high experts about memory tagging, we can see some code. So MTE has some new opcodes, some new instructions, of course. Here you can see IRG and STG. IRG gets a pointer, generates a new random tag, and sets this new random tag at the MSB part of your pointer. This handles the logic tags. STG takes a tagged pointer and sets the MSB value in its pointer as the physical tag in the underlying physical memory. This handles the physical tags. And now we can write some code. So the first thing that I'm doing here is just check that the underlying CPU has support for MTE. If not, we just get out. Now I call PR control because I want to configure my process to support TBI, MTE, and some past tense stuff. And you can just see this send flag, which means that we have synchronous mode, okay? We have synchronous exceptions. And now I call mmap because I want to map one page that is prot read, prot write, and prot MTE. This flag just tells the memory management, hey, please make sure that this page will be supported with MTE. And now we got a pointer to our new page, and we can write 2 bytes and read 2 bytes, and everything works. The tag is now 0, because all the tags by default are zeros. And now I want to set one tag, one single tag. So we execute IRG, and then STG. And now I print out the pointer, so you will see that it is like a tagged pointer. And I write the character C, and I read 2 bytes, and again, everything works. Okay, great. And now I want to intentionally trigger a segfault. I want to trigger a segfault to show you that everything works just as we expect. So let's write the character D, 44, into offset 16. This is guaranteed to segfault because we only set one tag, and each tag is for 16 bytes of aligned physical memory. And because we did not set the tag, the physical tag at this offset, it will still be 0. But the MSB part of PTR over here is still some random tag, right? So this will segfault. And if you try to execute code, this is on my Ubuntu Docker over the M1. So if you just try to execute it natively, you'll see that MTE is not supported because the M1 does not support MTE. But QEMU has all of the support for MTE with the emulation of the feature and all of the support in the memory management and stuff. So we just can use that. This is what we do in this talk. And as you can see, it works just as we expected. PTR got the tag of 1 by random. OK. But it's not enough. I need to show you with the GDB that the segfault is indeed on the store byte instruction. So let's execute it again. This time with debugger attached. By the way, note that PTR got the tag of 7, which is great because it was 1 before, and we do expect to have some source of randomness with the tag. And let's just attach a GDB, and you can see that the segfault is on the store byte instruction. When you try to write to offset 16, X9 is 44, the character D, and I just dump here the memory, so you'll see the TBI works just as we expect. OK, applications. MTE is clearly a great tool for testing. It's actually a very good alternative to ASAN because it has much smaller code size, which is great. And MTE is fantastic for finding bugs in production. This is actually what MTE was built for, right? Because MTE should have much better performance than all of the software equivalents. You could hopefully enable MTE in your production environment, and now you are much more likely to trigger some bugs that are much less likely to be triggered in your testing environments. And even though MTE was not designed for memory safety mitigation, we still see some potential, some interesting properties that we want to get from MTE for memory safety mitigation. And it's very important to be fair and honest and realize that because MTE was not designed for such purposes, it won't be a perfect candidate, which is good because otherwise I have no reason to be here. And this is something that I really want you to just like keep in mind. MTE has 100 binary compatibility with like existing code, almost 100. So it means that it won't be perfect for memory safety mitigation. Okay, now if we want to talk about like memory safety, we need to talk about heap safety. So clearly I need to implement all of the support in the memory management and in all of the allocators, because the allocators are the ones that generate new allocation. And we need the allocation API to actually retag all of the memory lines in your allocation, right? And we clearly need to get a tagged pointer back. Now, this is optional. On free, you could actually retag allocations on free. This will help you to catch some use after freeze even before reallocation, which is really, really nice. Now, this is critical with DLmalloc and with some other like allocators that has some pointers inside of like free chunks. But if your allocator don't have pointers or secrets inside like free chunks, you could give that up and you'll get all of the performance back, because retagging allocations is expensive. This is, of course, up to you or up to the vendor. The TLDR is that we get probabilistic mitigations for most of the memory safety bug classes, and I want to show you some examples. So if you just try to allocate some chunk on the heap and read or write out of bound, you are very likely to segfault. Actually, with a probability of 15 out of 16, you will crash, because the tag out of bound is very likely to be different. Same goes for use after free. If you do retag allocations during free, you are very likely to crash, because if you do malloc free and then try to read or write through your dangling pointer, the tag is very likely to be different. Okay, now, it's true. MTE mostly gives us probabilistic mitigation, but we still believe that we can get one deterministic mitigation, very specific one, out of MTE, and this is for very specific bug class. This is for strictly linear overflows or underflows. And this cannot get any simpler. We just go to the allocation API, and we modify it such that it will assign random tags for all of the allocations that it generates, with one minor restriction, that adjacent allocations always have different tags. And this is super cool, because now it actually breaks exploitability of all of the memcopy style bugs, right? So now we could actually take a bunch of bugs and tell people that, hey, on this new piece of hardware, these bugs are not exploitable by definition. And it's not a question of bypassing this mitigation, because the CPU, the architecture itself, will raise an exception on the very first byte that you read or write out of bound. This is insane. This is really powerful property to have. Okay, so here, it's the value of MTE as the MSRC sees it. You can see it's the like, bug classes that it mitigates. We talked about probabilistic mitigations and about deterministic mitigation, and now the actual fun could begin, finally. Okay, so every time that you build a new mitigation, it's mandatory. It's necessary to consider some like bypasses and weak spots, and etc. And in my own opinion, one of the best ways in order to achieve such evaluations is by writing exploits. Also, building exploits is the bare meaning of life. So we have a really nice opportunity here. And I just want to set up some rules, okay? So precise mode, which means synchronous exception, MT is always in in place. Clearly, like adjacent chunks have just different tags, because why not? Calling free with an incorrect tag segfaults. This is really reasonable, right? And I want to mention here that I use QEMU for all of the memory management support and for all of the emulation of the feature support. But unfortunately, glibc don't really have stable and official support for MTE. So for this research, I just built my own wrappers on top of glibc, with malloc, realloc, strdup, free, and basically everything. So in my own implementation, I made sure that calling free with an incorrect tag segfaults. I think that it's very important. And clearly, I only tag the heap. Okay, so let's talk about corruption of pointers, right? With MTE, we can corrupt pointers, because the logic tags, all of these MSBs in all of the pointers, are clearly readable and writable. So if I can leak pointers, so if I can leak tags, I can fake pointers, right? So if you want, for instance, to just corrupt some absolute 64-bit pointers, you can do that as long as you know the tag of your dest address. If you want to do this trick that I personally find very, very useful to corrupt the LSB part of your pointer, and just move it backward or forward in memory, you can still do that as long as you make sure to not move your pointer out of bound, or that you do move it out of bound, but you know that the tag at your out of bound memory area is the same. Intra-object corruption, this is a really nice bug class of bugs. This is the case where you have a really big structure and you have an internal like buffer or array or container inside of it, and you can trigger out of bound from your buffer. Now, as long as you never trigger out of bound from the entire structure, from the entire allocation, MTE has nothing to do about it, because from the allocator point of view, you didn't actually trigger out of bound, right? And inside the same allocation, all of the tags have to be identical. So intra-object corruptions are clearly exploitable deterministically with MTE. Now, leaking stuff. Information disclosures are really problematic for MTE, which means that it's great for us, because if you can shape your heap and leak a lot of pointers, you can know a lot of tags. And with the knowledge of the tags, we can fake pointers. And generic information disclosures are not the only thing that I'm concerned about. Just think about all of the speculative execution variants that we see new stuff on the daily, right? Just think about many side channels, right? Everything that leak you pointer give you tag, which is the knowledge, which is the secret that you need in order to fake pointers. And just consider this really classic bug in like JavaScript where you cannot control the base, but you have full control over the index or offset that goes like out of bound. If you can trigger side channels, you can know tags, and now you can choose your out of bound index to be to a memory area that you know that has the same tag as you. And this is how some probabilistically like mitigated bugs could be deterministically exploitable. And I think that this is really cool. Now, type confusions, of course. MTE has nothing to do with type confusions. They are absolutely exploitable deterministically. I just want to mention here that I'm not considering here like type confusion scenario that you built on top of like other bug. If you have some out of bound or some use after free and you created some type confusion scenario, your first order primitive will be probabilistically mitigated. But if your first order primitive is just a beautiful, beautiful type confusion, it's absolutely deterministically exploitable. And now the actual talk could begin, finally. So let's see some practical examples. As I've said before, we need support for MTE, right? So QEMU has all of the support for the memory management, and it works great, and the emulation of the feature, of course. I built my own wrappers on top of like glibc for this research, works great, and now we can begin. Now, before we start to write exploit, I just want to show some examples for famous bugs, CVEs from real life that are deterministically exploitable with MTE. The first one is a very famous one. I'm sure that you've seen it. This is a horrible, horrible bug in like NSS found by Tavis Ormandy, GPZ, great find. This is a great example for intra-object corruption. You have fixed size buffer with full control over the content and length and stuff, and you can actually trigger your like overflow inside the same structure. So this bug is clearly exploitable with MTE. We don't have time to cover this in detail, but you can visit the blog post by like GPZ. It's really, really good. Check this out. The second bug is an amazing find by Salo. Again, GPZ. This is a beautiful bug, one of the most beautiful that like I've seen, really. This is a great example for straightforward type confusion. This is in like JSC, and I'm really sorry that we don't have time to cover this because it's so, so beautiful. But again, check out the amazing like BlueHat talk. I like about it. The first order primitive here is basically fake obj and other of, which are clearly everything that you need in life. And I actually really wanted to build the demo in this talk about this bug, but unfortunately, JSC does not have support for MTE. And while I was very happy to build this really simple wrappers on top of like glibc, porting JSC to support MTE is not something that I find really interesting, so no. But I just want to mention here that because we know how to exploit this bug, and we have a type confusion, we could maintain this property, and this is the like, important part, we can maintain this property that we never dereference a pointer without being absolutely sure that the tags are identical. And because you have a beautiful type confusion, you can leak a lot of tags. Okay. And now the really interesting part begins. I want to show you some exploit example, like end-to-end. So we are going to exploit a pawn challenge from 2020. Some metadata and some info about the challenge. It used to run on like Ubuntu, 18.04, and therefore the intended solution plus the published solutions only targeted this version. They just did a raw double free on Tcache. It was possible 500 years ago, but it's not like possible anymore. So all of this stuff will just crash for you, deterministic abort on Ubuntu like 2004. And also the challenge lacks a lot of mitigation. So I just took out one wicked. I enabled all of these mitigations, and I solved it for like Ubuntu 20.04, and because the latest version of Ubuntu has some further hardening, I solved this for this version as well. All of that is like already published in my blog post with all of the exploits. You can check it out. But right now, I like actually want to cover the challenge, exploit it without MTE, and then enable MTE, see what breaks, and bypass this. And we have 18 minutes, which is great. OK, so we have a challenge that implements a list of elements. Each element could be long, double, or a pointer to a string. And our data structure supports add, get, edit, and delete operations. OK, cool. And I just want you to keep in mind this structure in the middle, the list one. It has a pointer to the array of the keywords, which are all of the elements. It has size, which is the current number of elements in the array, and it has the maximum capacity. Now, a very trivial problem here is that when you do get and edit, the code has no way to know which type of element it is interacting with. And the CTF author just solved this in a really nice way. When you do get and edit, the code asks from you for both the index and the type of the element. And this is how you have a really straightforward type confusion. So the first primitive that we have is that we can treat a heap pointer, as an integer, and we can read it, and we can treat an integer as a string pointer, dereference it, and read its content. So basically have arbitrary read by design. This is just to give you a good sense of it. This is the get function from the challenge, and as you can see, the challenge asks for us for the index, and then for the type, and then it just do the job. OK, we also need the ability to corrupt memory. So there is another vulnerability in the delete function. When you delete some elements, the challenge needs a way to know if it's an integer, which does not require a free, or if it's a string pointer, which does require a free. And it's true that the code could ask from us for the type here as well, but it doesn't. Instead, it maintains a global array that's called fpool. This array just contains all of the virtual addresses of all of the allocated strings ever. So every time that you add a new string, the address of the new string goes into this buffer. Now, this buffer is static inside, and it doesn't increase. And also, the challenge does not remove pointers after it free them, and it doesn't null them out. So besides the obvious leak that you have here and many, many other problems, you can just call free as many times as you want on the same virtual addresses. Of course, as long as this virtual address is in the fpool array, or in other words, as long as it's used to serve an allocation of a string. OK? Very simple. And this could be converted into an arbitrary free by just making sure that the object that you want to arbitrary free was used to serve an allocation of a string from before. And this is the code. This is from the list add function. As you can see, each time that you do add of a new string, we call just like str dup. We add the new string to the list data array and to the fpool array if we have enough space. And when you delete some element, you just scan the fpool array to see if you deleted keyword is inside the fpool array. And if so, this indicates that it needs to be freed. OK, so we know that we work with strings, so we can't have nulls in the middle. There is no coalesce and no consolidate in the Tcache, and now we could start to exploit it. And as I've said many, many times before, the meaning in life is to get arbitrary read and write, so let's start by arbitrary read. This is possible by design. You just take the address that you want to arbitrary read, you add it as a type long, you call get with type string, you have arbitrary read. The reason that I call delete here is just to make sure that this cute Python function won't affect on the internal state of the array. That's it. OK, so we have an arbitrary read, and we can leak all of the heap addresses because of the type confusion, so we can get libc, right? Because we can just free some chunk into the unsorted bins. You have a pointer to the main arena symbol. You just leak it, and because libc has a pointer to environ, I can leak the stack as well. OK, now we need to get some arbitrary writes, of course, and we cannot do the double free attack because, again, it was mitigated. But we can do something else. We can just corrupt the FD pointer inside of a free chunk. This will give us the ability to control over the next return value of malloc. This is a very common exploitation technique. In Linux, you can see it basically in every pawn challenge, in every CTF. And the only question here is, how would you gain the ability to write into a free chunk? And this is very simple. I just need to make sure that the list data, the array of the elements, reclaim a freed string. Because then it's in the fpool array. And now we can call arbitrary free on that. And I can write through the dangling pointer into the FD value. So this is the heap. The first structure to get allocated is the list, and then we have the array. Now I want to add a string, and I want to free it, and now I want the list data to reclaim the freed string. So let's just add more elements. We have reallocation, and I can do more elements, and we have another reallocation, and now the list data is in the F full array. Call arbitrary free, and use edit to corrupt the FD, and we have arbitrary write. Okay? Now on Ubuntu 20.04, you can corrupt the free hook symbol. Past 10, it's over. On Ubuntu 21.10, the malloc hooks were mitigated, sadly, so you can just do ROP like on the stack, and it's a game over. This is the exploit. This is how it looks like. Again, it's all published. And now we can begin with MTE. So I want to enable MTE and see what breaks. And because I want to have a soft landing, let's just enable MTE and assume that we only retag allocations during malloc, but not during free. So, and because we don't have time, we absolutely don't have time, we only do the exploits end-to-end on Ubuntu 20.04, so I will corrupt the free hook function, but the same tricks, the same primitives, the same everything could be repeated to do ROP on the stack on Ubuntu 21.10. So we have some news. The good news is that all of the dereferences to free chunks are safe because we did not retag allocations on free. The interesting news is that our arbitrary write is via malloc, right? We control the next return value of malloc. And malloc retag the entire allocation, the entire memory that you get. So if you target with your arbitrary write the stack of some globals, you are fine because it's not a tagged memory. But if you tag the heap, you actually retagged it under the legs of some other thread. So this could be problematic. The really bad news is that both arbitrary write and arbitrary free are very likely to crash, and I want to show you why, and I want to show you how we can bypass this. So why the arbitrary write fails with such high probability? So just a short reminder, we just trigger arbitrary free on the array of the elements, right? And now we just corrupt the FD pointer, we reallocate this array, and now the next return value of malloc is fully under our control. The problem is that your allocation primitive actually works like this. You call STRDUP, and now you add the new string to the list data array. This is really funny, because the call to STRDUP will reclaim the list data allocation. So the allocator will retag all of the memory lines of this allocation. And now the physical tag does not equal to the whatever MSB value of your dangling pointer. So this is really, really likely to crash. And this is actually like what happens. If you just attach GDB to your exploit, you can see that inside of list add, we just segfault, when you try to add the list data, which is 14.2FO, to itself at like index 2. And you can see that the two tags here, 6 and D, are just different. Okay, we can fix this, no problem. But before we do, I just want to show you really quick why the arbitrary free crashes. The arbitrary free, again, a short reminder, works as following. You just malloc a string, you leak its address, you free it, you do shaping, so your array will reclaim the string, and now you call arbitrary free with the absolute pointer of the string that you leaked. You cannot call free on that. This pointer has a different tag than the current existing physical tag of the new array, right? And again, calling free with an incorrect tag will segfault. So if we leak the current tag of the list like data array, we could call arbitrary free. And we are very lucky because we have arbitrary read, we have a really deterministic allocator, and we know exactly where the list structure is. This is the structure that I showed you at the beginning of like our talk. And the list structure clearly has a pointer to list data. So let's just use arbitrary read and leak this tag, and we are done. So not really, because you cannot trigger arbitrary read on the list structure because we have no idea which tag it has, right? This address is not in the array, so the type confusion does not give me this address. But this is really funny, because we know that the main stack frame has a pointer to the list structure, and I know where the stack is. I have an arbitrary read, so I can just scan the whole stack remotely, and I can get the pointer to the list structure along with its tag in the MSB. And now I can do another arbitrary read to leak the tag of the list data, and this works. So, okay, this is really nice, and we actually stop like crashing. But if you will take a look, you'll see that the exploit fails because the array has not actually been freed. And this is because in order to the free function to actually get called, our pointer with the new tag has to be in the F full array. And there is no reason it will be there, because in my exploit, in my shape, I just allocated a string and I free it once. This is the F full array. 14.2FO is the list data. And we only has one instance of it with only one tag. And with extremely high probability, this tag does not equal to the new tag that the list data array got. Okay, we can fix that. Right? Just like instead doing malloc free once, let's do it 200 times. Let's have a lot of pointers of the same virtual address in the F-pool array with many, many different tags. And with extremely high probability, all of the 16 possibilities of the tags will be there. And now the arbitrary free is saved, and like everything works. And we actually have now an exploit that works with a probability of 1 out of 16 instead of 1 out of 16 squared. And it's really nice, especially compared to the really minimal efforts that we just did. Now, I really want to have demos, but instead I will do all of the 3 demos together because we don't have time, so I have screenshots. But again, you will see it live in about 2 minutes. This is the base exploit. This is what happens if you just run my exploit in a loop, okay? Hopefully that some good random happen. And after 153 times, it just so happened that both the tags in the arbitrary free and in the arbitrary write are okay. And we got a shell. If you implement the bypass of the arbitrary free that we just saw, then it works after 4 times, which is really nice. And now we can fix the arbitrary write, and we'll get deterministic exploit, and then I could finally get my whiskey. So, just like a short reminder, what's going on here is that we reallocate the list data, and therefore the allocator retag the entire allocation, and then we write the new string into the list data array. This store bothers me. The fact that the challenge writes the pointer to the new string into the newly tagged chunk really bothers me. So I can just shape my heap such that the list data won't be freed into the T-cache, it will be free into the small bins. And now I can just reclaim part of the allocation, and therefore the allocator will just retag the beginning of it and not all of it. Let's see it in action. So this is the heap. The background color, thank you so much, Ida. The background color is the tag, okay? So we have 3 elements, and I want to add more. I want to add more because I want the list size to be really close to the end of the array, to the end of the allocation. And now I call arbitrary free. Because we do not retag on free, the tag remains the same, but this chunk is now freed. And I can add one more string, and this is the super important part. We add one more string, so the allocator retag the beginning of the allocation, and it stores the pointer to the string to this offset. But this offset has the same tag as the dangling pointer. The physical tag and the logic tag are identical, so we are safe. Okay, so now we can free this string and corrupt the FD pointer, and we are done, right? So not really, because again, in order to corrupt the FD pointer, we need to write through our dangling pointer. But the MSB of the list data does not equal to the new some random tag that we got. But we have a type confusion, and I can leak this pointer. I can leak the S1 along with its tag. And I can check if this tag is identical to the tag that I already have. And I can do it again and again and again, malloc free, malloc free, malloc free, and until I get the same tag. And now we have a full exploit that works deterministically. And now let's have some fun with some random. If we can go to the demo, please. Might take some time. OK, awesome. So let's start the Docker. OK, so we have BlueHat demo, nice. And we have BlueHat, and we have MTE POC. And I just want to build the challenge. So you'll see that we have here the RMV 8.5 plus memtag. This is how you build with MTE. Okay, and we have 3 exploits. We have the base exploit with 0 awareness for MTE. We have the arbitrary free works, as I've showed you. And we have the deterministic exploit. So if we just try to run the base exploit with 0 awareness for MTE, it will run and run and run, and it fails 20 times, 30 times, 40 times. We can keep it going, but it doesn't really interesting to play with random numbers. So let's just run an exploit that has much better probability to succeed. Yep, sometime the Docker does funny stuff. And again, it's random, but after some attempts, OK, so after 2 attempts, it's work, and we have the flag. And you can see that it works after the 2nd attempt. And just to do it correctly, thank you, we can do the deterministic exploit. It ran only 1 time, and it works. And this is the part this is the part when we do like malloc free, until we got the same tag. All of this code will be published with the slides. I really encourage you to get your hands dirty and to try to mess around with it. It's like really fun, and we can execute it again and again and again, and it will always work, because we only dereference pointers where we have the knowledge that the tags are identical. It will always work. OK, now we can go back to the slide. Thank you. OK, so let's face the fact that not retag on free with like DL-malloc is really unwise, because you have pointers inside of free chunks, right? We have the FD pointer that gives us like arbitrary right. So we really need to retag allocations on free, and this is what this sample show you. This show you that it's really important to retag allocations on free if your allocator has no awareness for security whatsoever. So if you do retag on free, this is what happens. The like leak of Eclipse will fail, right? Because we read the content of a free chunk, so there is a dereference there. And if you will try to corrupt the FD, you will crash again. So the entire exploit works with like probability of 1 out of 16 squared, and this is really bad. So the main messages here are that, well, that like MTE broke some of the exploitation method, right? For instance, every read and write into a free chunk are really problematic now. And the funny part is that it did not break the exploitability of bugs. Bugs are still exploitable, because first of all, you can do probabilistic exploits, right? And it will work eventually. It really sucks, but it will work. And second of all, this just was a CTF challenge. I only had strings here. And it's not even STD string, it's just buffer of bytes. But if instead of the add-on of like a new string with the str dup, I would actually like allocate a C++ object with a vtable, I could leak libc and I could bypass like the SLR without the need to like dereference free chunk. Same goes for arbitrary right. If you have many structures, as you do in like real life, you actually could to gain arbitrary right through these pointers, and you don't need to actually dereference free chunks. So this is why I believe that in real-life scenarios, type confusions, first-order type confusion will compromise your system. I just want to mention here that this probabilistic exploit could be really problematic with some daemon and services that keep relaunching like themselves. So if you are not in like a kernel like environment that you really don't want to crash, you have a problem. But on the other side of it, people that exploit bugs don't really want their exploits to crash with such high like probability. First of all, because it's really suck and it's really sad and it's really lame, and also because the like probability that your bug will get disclosed is much more high, right? This is a really funny part. We don't have time for this, so just check it out at home. But just like to sum up, we have probabilistic mitigations for most of the memory safety bug classes. We have one deterministic mitigation, really cute for copy and for like strictly like linear overflow and like underflows. And I have serious concern about information disclosures, about straightforward type confusions, and clearly about the fact that we only have 16 possibilities for tags. This is a really small number. But again, MTE was not designed for a memory safety mitigation, so it's fine. I just think that it's really nice to take a new silicon feature, enable it, and just mess around with it, see like what's going on. And I really hope that you have fun. Shout outs to all of my friends at MSRC, MSR, ARM, Cambridge, and like all of the stuff. Here are some links that you could follow. And thank you so much.